Welcome. This lecture describes a family of algorithms for solving the supervised learning problem known as stochastic gradient descent. Our objectives are to simplify the gradient descent update that we've looked at previously. And we do this by cycling through the data. So we'll review some common methods for cycling through the data, point out the benefits of doing this, and conclude by deriving a couple example algorithms. So the essential idea with stochastic gradient descent is to update the weights using only part of the training data rather than all of it, as we've looked at so far with gradient descent. So recall that we have some cost function f of w, which generally is going to involve a loss, L of w, which measures how close model or our predictions are to our labels or desired data, plus a regularizer that helps control the properties of the solution. Now, one way to solve this problem is to iterate through a series of gradient descent updates, because this is a convex function, so if we go downhill, we'll converge to the global optimum. So we're going to update wk plus 1 based on wk, and then we'll take a step in the negative gradient direction. We'll let the step size here be tau over 2, and del w f of w represents the gradient. So we've looked at a couple different loss functions. We could consider squared error, which just sums the errors over all capital N of the training samples. So we have labels d sub I and features x sub I, and we're forming the squared error, the difference. We can differentiate that, find the gradient, and it's just -2 times the sum di minus xi transpose w, quantity times xi. Similarly, we can look at hinge loss, in which case the loss function was a sum I equals 1 to n, the quantity 1 minus di xi transpose w, the positive part. If this is negative, it gets replaced by 0. And in this case, the gradient is just the sum from I equals 1 to n of negative the indicator function di xi transpose w less than 1 times x sub I. The point is, in both cases, these gradients depend on all of the data, all capital N samples. In stochastic gradient descent, we break our cost function up into a series of terms that depend on each data sample, and then we find the gradient associated with each fi, and we update our weights using this gradient. When we do that, we're going to cycle through all our data in a sequence which we'll call I sub k, where k goes from 1, 2, and so on. When we're looking at the value I sub k, we're updating our weights based on one sample labeled d sub I sub k and the feature x sub I sub k. And we're taking the gradient of this cost function that depends only on sample d sub I and x sub I. So this approach cycles through the training data. And there's several different ways of cycling through it. We could take a cyclical approach, which is sometimes known as incremental gradient descent, where we just walk through the training data in order sequentially. So suppose that capital N is 4, then we would choose a sequence. We would update with the first sample, then update the second sample, then update the third sample, then update the fourth sample, then repeat. First sample, second sample update, third sample update, fourth, and repeat again. We can define that as ik is equal to k mod n. Another approach is within each set of n updates is to reshuffle and do those in a random permutation sort of way. So I take my first 4, if n is 4, and I'm going to reshuffle them. So I might go through the first data sample, then the fourth, then the first, then the third, then I get to the next 4, and I reshuffle these again in a random way. And so that might be the second, first, fourth, third. Next 4, I reshuffle again, and we keep repeating this process, walking through the training data. The third approach, which is the inspiration for the name stochastic gradient descent and is what's most commonly associated with this approach, is to sample the data uniformly at random. In other words, I'm drawing my index I sub k as a uniform sampling from the integers 1 to up through n. In other words, I'm uniformly sampling my training data. So in this case, I could choose I sub k to be 2, 1, 3. I might pick 1 again. I might pick 4, and then I get 4 twice, and then 2, 3, 1, 3. Each new sample is independent of the previous sample, so we can have repetitions. So in each of these cases, we're going to update our weights using the negative of a step size, which we'll call tau over 2, times the gradient with respect to w of f sub ik. On average, this results in the same gradient that we had before with respect to the total cost function f of w, where here the e denotes the expectation or the averaging operation. These different approaches have different characteristics, and whilst the stochastic gradient descent approach is most commonly used, it's difficult in general to say that one is optimal where the other is not. One thing we can say about stochastic gradient descent is that it does satisfy this property of the expected value converging to the gradient normalized by n. So the main reason for doing this is to reap some computational benefits. First of all, computing the gradient with respect to each training sample is generally much easier and faster than computing the gradient with respect to the entire set of training data. Second, in large problems, you may not even be able to store all the features for the training data in memory at once. And by using stochastic gradient descent, we can read in the data that we want to use to update and then discard it and sequentially read it in and never have to store it all at once. Another feature is that this noisy gradient operation tends to introduce some added regularization. And this is a topic that's under current investigation, but it avoids some of the sensitivity of gradient descent to ill-posedness in the least squares solution. So the gradient, when we consider the entire set of training data associated with the global cost function f, is going to point in some direction that represents the downhill direction involving all of the training data. Now, when we use stochastic gradient descent and we're computing gradients based on each sample of the training data, then the gradients can point in apparently noisy or random directions. I might have one training sample, the gradient points to the right, another training sample, the gradient points up and to the left, and so on. On average, over all the training samples, these gradient steps associated with stochastic gradient descent go in the same direction as the noiseless gradient associated with the entire training set. So let's begin with an example of ridge regression. Recall here that our cost function is the squared error loss summed over all our training samples plus the 2 norm of our weight vector. I can break this up as a sum of cost functions that depend on the training sample I by incorporating 1 over n into the regularization term, so that I write this as a sum from I equals 1 to n of the quantity, the squared error at each sample, plus lambda over n, the 2 norm squared of the weights. We can take the gradient of this using techniques we've already developed. If I take the gradient with respect to w of di minus xi transpose w squared, that's going to give me negative 2 times di minus xi transpose w times the gradient of this quantity with respect to w, which is just xi. And we'll take the gradient with respect to w of the second term, and this is just 2 lambda over n times w. Hence our gradient update takes the form w at step k plus 1 is w at step k minus tau over 2 times the gradient of w at step k with respect to the training sample I sub k. So we can substitute in for this gradient and write that w at step k plus 1 is just w at step k plus tau times the difference dik minus xik transpose times wk, quantity times xik. So that takes care of this first term. And then we're going to subtract tau lambda over n times wk. Now if you look at this particular update, you see that the only thing we have to do is form the inner product of the feature with the weights and multiply this scalar times this vector xk, and the rest are subtractions. So there's order of m operations since w is an m-dimensional vector. In contrast, if we look at this similar case of full gradient descent where we use all the training data at once, in that case the gradient update ends up being plus tau, the matrix A containing all of the features or all of the training data, transpose times the quantity AWK minus D. And A is an n by m matrix. So here we're going to have to multiply this matrix times this vector, and that operation involves order n operations since A transpose has n elements in each row. So this is considerably more computationally intensive. It also requires that A be stored in memory at once, whereas we don't have to do any of that with the stochastic gradient descent approach. We'll conclude with the second example of deriving gradient descent for the lasso. In this case, our loss function is the squared error, again, summed over all n training samples, plus we regularize with the L1 norm of the weight vector. So we can write this as a sum over individual cost functions with respect to the training data sample I by writing Fi of W as Di minus Xi transpose W quantity squared plus lambda over n times the 1 norm of W. Now in this case, we're going to take the gradient of the 1 norm, which we haven't done before, and we can write out the 1 norm as a sum from L equals 1 to m of the absolute value of W sub L. So we're taking the gradient, we're going to differentiate with respect to W sub L. The absolute value has this joint here and thus is not differentiable. So we're going to have to use a subgradient approach. So we'll define the derivative of the absolute value of W sub L with respect to WL as the sine of WL when WL is not equal to 0. So that's going to either be plus 1, we're on the right, or minus 1 when WL is less than 0, hence we get the sine. And the subgradient says that we can choose any slope that we want when WL is equal to 0, as long as that slope is between minus 1 and plus 1. It's very popular in this kind of a scenario to choose a slope of 0 when W sub L is equal to 0. So we'll write the gradient of the 1 norm as the sine of W, with the understanding that when any element of W is equal to 0, we use 0 for the gradient at that point. So this allows us to express the gradient of the cost function for the ith training sample as the derivative of the loss function, or the squared error, which is just negative 2 d sub I minus xi transpose W, as it was before, times x sub I, plus lambda over n times the gradient of the 1 norm, or sine of W. This leads us to the gradient descent based algorithm. W at step k plus 1 is W at step k plus tau times the quantity dik minus xik W at step k times xik minus lambda tau divided by 2n times the sine of wk. Again, this is a very simple update for each of the training samples, since all we have to do is this order m inner product represented by xik transpose times wk, and then we have to multiply this scalar times the m-dimensional vector xik. So we'd cycle through all the data in some random order associated with this index ik, and this gradient descent approach should converge to the same solution as we obtained using all of the data at once. It's quite a bit more challenging to analyze the details of the convergence behavior in this case, and that's a problem that remains of current interest.